Okay, well, we are very happy to have Gabriel Cuomo from Simon Center and Stony Brook, and he's now actually in Zurich, as he just told me. And he's going to tell us about why, I don't know if it qualifies as review, anyway, some overview of his work and other people's work on the large charge sector of CFTs. Please, Gabriel.
Okay, thank you for the invitation. Thank you for this nice series of seminars and lecture, which have been extremely nice and are still be extremely nice. So today, as Lava said, I want to make some overview of some results in the large charge sector of conformal field theories. The goal will not be to present a complete review, nor to present many new results, but just to try to put in a coherent picture a number of results. I'll do mention some new results. I'll also try to mention some open questions, which can be of slightly more general interest. And okay, so that's basically a wishful overview of my talk. So after some introduction, I'll start reviewing some progress in the epsilon expansion that will serve us as a motivation for what is the general picture and the general results which we expect to apply also in strongly coupled CFTs. I'll try to show, at least review and extend some results to see how these results connect with the large spin results, which have been more carefully analyzed by the Bootstrap recently. And if I'll have time, and I hope I'll have, I want to mention also something about large charge operators in theories with moduli spaces, mostly reviewing the work of Simon Hellerman in those theories, which are mostly supersymmetric, but some ideas are general, and I hope I'll have time to convey that message. So let me start with the introduction. So it's a fact of physics essentially that large quantum numbers often entail some simplification in the description of a theory, the typical example being the large angular momentum limit of the hydrogen atom, which entails a semi-classical limit. In conformal field theory, this is no exception, and this has been first realized systematically in the context of the large spin. So large spin operators, mostly double traces, can be analyzed within the Bootstrap itself. And then there is a 1/j expansion, but the physical picture underlying it is the one which was proposed by Lambda in 2007. And some similar pictures were being recently proposed for heavy operators, in particular matrix element of heavy, light, heavy operators. And by Hellerman collaborators also for the case of large internal charge in theories with internal symmetries. So the key idea, again, in all these examples, I think is the state operator correspondence, at least for the physical picture. And just to review how this works out in the large spin case, and the idea is due to Aldemel-Dasena is that large spin operators, at least some large spin operators that you would intuitively call double trace, can be thought as to leading order some free moving, fastly spinning particle on the cylinder. And therefore, their energy will be approximately given by their free energy, which is twice their mass, the scaling dimension, plus the angular momentum, And corrections will be small. And to see this, one is better to go to some Weyl equivalent manifold, ADS free times SD minus free. So there is a Weyl map just between flat space and this manifold, it's a fact. And in this manifold, it turns out that the distance between the two particles is proportional to the logarithm of the spin. And the gaps is given instead by the twist spectrum of the theory. So since every CFT in dB greater than 2 has a twist gap, correction will be due to Yukawa potentials, and we go like e to the minus gap times the distance, which translates through this equation here in 1/j times tau corrections. So of course, remarkably, then the Bootstrap computed this factor here precisely, and but this is somewhat, I think, special of the large spin case, because in the large spin case, conformal blocks themselves carry the spin quantum numbers, and this makes it feasible to a crossing equation analysis. But the physical picture instead just relies on state operator map and effective field theory. So the goals of the large charge expansion conformal field theory are similar. So just to set up what one expects to do, one takes a d-dimensional CFT with some internal symmetry G, calls Qi is the global Cartan charges of the group, which you might also include spin in this set. And the lowest dimensional operator with fixed charges Q will be some operator OQ. And the idea is that when the representation in which these groups transform is large enough, so when the Cartan charges are big enough, then you will be able to compute semi-classically correlators which involve light operators insertions in between OQ and O dagger Q, essentially. And this is the idea of Ellerman, Orlando, Reffert, and Watanabe in 2015. So let's see how this is borne out in a simple example. I know some of you already heard this often, but I think it's still useful to put it in order. So consider the simplest example one can study the large charge operators is clearly the Wilson-Fisher fixed point with U1 symmetry. In general, is the simplest interacting conformal field theory thing we know that we can study in 4 minus epsilon dimension. And the goal will be to compute the scaling dimension of the operator phi n for small coupling, but large charge, such that the product of the coupling and the charge is fixed. And it's going to become clear in a moment that this limit is an interesting limit. And the idea is that we illustrate the transition from a vacuum or strongly or non-universal regime to a simpler universal regime. So just me review why this limit is interesting. By the way, interrupt me any moment with questions, of course. So the reason why this limit is interesting is that an operator phi n in the epsilon expansion has n legs. So if you start looking at loops diagram, you will see that at one loop you have correction going like lambda n square. At two loop, correction going like lambda square n cube, just because of the way you can connect the diagrams. You have all these factorials popping out, and so forth, so lambda cube and 4. So in general, the perturbative expansion will be something like this. Loop order L, there will be a polynomial of order L in N. And the perturbative expansion must therefore break down when lambda n is of order 4 pi square. So this doesn't matter how small the coupling is. If you can take the charge large enough, you cannot do Feynman diagrams. And but okay, this problem already suggests it's cured by itself. Let's just try to group diagrammatically all the terms which have the leading power in n in this expansion here. So the lambda n to the L, lambda n to the L minus 1 here. And this essentially amounts to reorganizing the series in this way. So the f tilde 0 lambda n here will be this sum here. The f tilde 1 here will be this sum here, and so forth, so on. And if you multiply and divide by lambda, you formally find that you can reorganize, even though now it's not clear yet how to compute, the series as a series at small lambda and fixed lambda n. That's why I said at the beginning, this is the limit I want to look at. And yeah, from now on, I will drop the star from the lambda. And this result here is very nice because it suggests, well, this rewriting here is very nice because it suggests an obvious way to perform this calculation, which is through semi-classics. So you take the correlation function phi n phi bar n, as you write it as exponential of 1 over lambda times an action minus lambda n log of the insertions. So you see right away that if you somehow were able to do saddle point on this effective action here, which includes the sources, it depends only on lambda n because I scaled fields so that one of the coupling appears in front of the action, you would get by saddle point precisely the expansion which I wrote over there. So the right thing to do here is to do semi-classical analysis. So, okay, in fact, one could do the analysis right away in the path integral I wrote before, but it's more convenient, at least for the sake of the presentation of this talk, to do it in a slightly different way. And again, to use the state operator map, which makes more manifest where we are going. So let us recall that phi n is the operator with lowest scaling dimension with U1 charge n. And therefore, we can compute its energy by simply considering an arbitrary state of charge n on the cylinder and considering the Euclidean evolution operator in the large time limit. This will project, just by plugging the identity here and here in terms of complete basis of state, into the ground state in the large time limit. And we will be able to read the scaling dimension from the usual state operator map. Then, so all the task here is to write the appropriate state psi n, and this is also very simple to find an obvious guess. You just recall that in quantum mechanics, angular momentum m states are like e to the I m phi, where phi is the azimuthal angle. So you do the same thing in field theory. You decompose phi as a radial mode and a Goldstone mode and a, well, phase mode. You fix the value of the radial mode at initial and final time. It's just a choice. You could have chosen something different. It would have not been important, but it's simpler. And you put some factors e to the n integral over the volume of chi at final time and chi initial time, which project onto charge n states. That's just e to the n phi in quantum mechanics. So this is your path integral. And now we can do semi-classics in this path integral. This turns out to be easier. And then you can find a saddle point solution. So, okay. So the saddle point turns out to be very easy if you tune the value of f, which I mentioned before. If you don't tune it, it will reduce to this one as soon as you go far away from the initial and final time. So, and it's just given by the Goldstone mode being moving linear in time. The I is because you are Euclidean. We are in Euclidean, rho being constant. And the value of mu and f are found by solving some algebraic equations which follow from the equations of motion. I won't display them here. But what is important is that this profile breaks spontaneously some symmetry. So a conceptual point which will be of some importance is that we are working at finite volume, so there is no symmetry breaking. But nonetheless, once you make a saddle point, the classical profile prior to integrating to over the zero modes will break some symmetries. And the symmetry in particular will break time translations because it depends on time. The U1 symmetry because rho takes some value, but it's in such a way that the trajectory is stationary, meaning that there is a linear combination of time translations and U1 symmetry, which leaves invariant this profile. And this is what defines as superfluid from a field theoretical perspective. And the result, again, you find it by expanding the path integral. The leading order will be the classical action. The one loop will be the one loop determinant. And everything will depend on lambda n and will be an expansion in lambda. And in this paper with Gilles Badel, Sashamoni, and Riccardo Lattazzi, you find the explicit expressions of 3-level and one loop. So one point, I could now give you an exact expression, but I will not do that because it's not very instructive. I'd rather focus on the two opposite limit, the one of small lambda n and large lambda n, in order to introduce the effective field theory. So the small lambda n regime, and if you reshuffle a bit the result, will look something like this. And as you see here, there are two kinds of errors in this result, two kinds of things I'm neglecting. One is this. So this is epsilon square n. So in the way I'm computing something which is 1 over epsilon times function of epsilon n and function of epsilon n, and neglecting something which is epsilon times function of epsilon n. So this is two loops in the semi-classical expansion. And therefore I didn't compute it because, it's just harder. Instead, this epsilon cube n to the 4 is just because I neglected higher order in the small lambda n expansion. But it's there in the full expression. It's just because I truncated the expansion. And what's important is that this result here perfectly agree with diagrammatic calculations, which are, this is a two-loop diagrammatic calculation. And the two-loop diagrammatic calculation also contains the epsilon square n term. Notice there is an m in front. But besides this term that I didn't compute in the semi-classics, all the others agree. So this validates the semi-classical idea. At the physics level, what I want to remark here is that it's about the spectrum. So you can now look at the spectrum of excitations around this profile and ask what is the gap of the modes. So one of the modes, I said we will break the U1 symmetry. So one of the modes in the infinite volume limit must be a Goldstone boson. So that will have a gap order 1 over R always. So the interesting question is about the gap of the radial mode around this profile. And this gap in this small lambda n turns out to be order 1 of the radius as well. This is, okay, this could have been expected because it is a regime where you can do Feynman diagrams, so you don't expect anything peculiar to happen. So the theory just consists of two like modes, and you should do calculations in the full theory. And this is drastically different than what happens at large lambda n. At large lambda n, you have an expansion which takes this form. So the leading term will be like n d over d minus 1 with a coefficient which depends on epsilon. And then d minus 2, d minus 1, again, coefficient depending on epsilon. And here I wrote down explicitly alpha 1 just for illustration, and alpha 2 was a similar expansion. And okay, so you see that the opposite regime, this regime cannot be reached by Feynman diagram. So it's very, if you would just add all the diagrams, this powers here, n d over d minus 1 would have been very non-trivial. But it actually is semi-classical, it's very easy to understand. It just follows from dimensional analysis, or if you want more precisely from the existence of a macroscopic limit. So for instance, to see this, if you can imagine taking the infinite volume limit, so radius to infinity, energy density, so epsilon tilde delta over RD fixed, and charge density fixed, then you see that this limit implies, if it exists with epsilon rho non-trivial, that epsilon tilde goes like rho d over d minus 1, which is precisely what you found there. What's a bit perhaps less trivial is about these bleeding powers here. And well, I mean, a way to start understanding them is to notice that in this regime, while the Goldstone mode will still be light, of course, so we still have a gap 1 over radius, the radial mode becomes heavy with a gap of order the chemical potential, which again by dimensionality should be like the charge density power 1 over d minus 1, so lambda n over 1 over d minus 1. And the fact that in this regime, the radial mode is very heavy suggests that you can understand this result via effective field theory ideas. And that's what I'm going to turn next. Okay, if there are no questions, I'll move to the effective field theory. Okay, so let me recapitulate what we learned and what we think is general of the calculation we just did. So we consider the Euclidean, so sorry, I'll now switch n to q. I forgot to update the slide. So charge now will be q. So we consider a CFT with U1 symmetry, and we consider the Euclidean evolution operator between two charge q state, in particular lowest dimensional charge q state. And we argued, especially in this example, that one expects this potential to be dominated by some classical trajectory. And the classical trajectory, in general, will realize non-linearly some of the symmetries of the theory. Even though there is no spontaneous symmetry breaking final volume, the classical trajectory will break some symmetries. This in turn implies, generically, that you expect a universal description in terms of the Goldstone modes implied by the symmetry breaking pattern of this trajectory. And the simplest, but not only option, is a superfluid profile. But essentially, in the case of U1 symmetries, staying away from the large n limit at least, you expect two possibilities, depending on whether or not the U1 is broken. If the U1 is broken, one would expect something like a superfluid. If the U1 is not broken, one might expect something more like a Fermi liquid, which is not semi-classical, but it's still weakly coupled. So the idea is that there will be a finite number of possibilities classified by the possible ways you can break this symmetry group, so conformal times U1. And this viewpoint has been emphasized in this very nice paper by Sasha Monin, David Piscalava, Riccardo Rattazzi, and Fiona Sable in 2016. So, okay. How do you do? So even if the theory is strongly coupled, I said we assume that we can describe some features of this path integral through effective field theory, and the effective field theory is specified by this symmetry breaking pattern more precisely, and we can use we can write effective field theory effectively in terms of a single Goldstone mode, and assume all the radial modes will be got at the most natural scale, which is the chemical potential, which is some power of Q. The exception to this rule concerns moduli in superconformal field theory, so concerns the case where you have additional symmetries, and therefore you can start having more universality classes from the symmetry breaking pattern. And therefore, the strategy will be just to write down the Lagrangian in a derivative expansion and compute from that Lagrangian. So this is the Lagrangian written in terms of the Goldstone mode chi. Chi is of order mu. So this term goes, the leading term goes like it's d chi to the d, so like mu to the d. And once you translate in terms of q, is qd over d minus 1. Subleading term will go like qd minus 2 over d minus 1. So you start seeing they match precisely what we found in the epsilon expansion. And next to subleading term will be powered again by 2 powers of q1 over d minus 1. So we can now use this action to compute the path integral and see if it matches what we found in the epsilon expansion. And this is precisely the case. You find this scaling dimension is up to some Wilson coefficient, because this coefficient here, C, C1, and C2, in the epsilon expansion can compute them, but for instance, the 3-dimensional O2 model, or in some other theories in which you might expect this effective description to apply, they just depends on the microphysics. And so I don't know any smart way to compute them. But up to these Wilson coefficients, you find the scaling dimension in a large charge expansion, as promised. And interesting, you find also some one loop contribution. One loop naively scale like q to the 0. And this is interesting because the one loop is independent of the Wilson coefficient. This is because essentially the dispersion relation of the fluctuation is independent of the Wilson coefficients. So the fluctuation determinant is independent. And therefore, they will provide some universal, in a sense, theory-independent result, well, within the universality class. And in odd dimension, particularly in equal free, the leading term will be q to the 3r, then q to the 1r, then q to the minus 1r. So there is nothing which can normalize the one loop Casimir energy. And this is found to be a number, which is given here.
Gabriel, can I ask a question?
Yes.
I think I probably did not understand fully why, or to which extent we're sure that this saddle point exists. I mean, in the 5 to the 4th theory, you showed it, like you have the explicit Lagrangian, and you could see, okay, if I take lambda to 0, I have a coupling. I take n large or lambda to 0, and then I get explicitly that there is I can write something like something big in front of the action. And in the general case, is it obvious that large Q leads to a saddle point, or is it
no, so it's not obvious, an assumption, if you want this expect.
Yeah, so can you say a little more about why do you expect this always, or except when there are moduli? I mean, if there are exceptions to these rules,
yeah. Well, I mean, okay, I think it's more come by experience. Well, let me think what is the best phrase to phrase it. Right, so I think the best way is if you think of a state as specifying some boundary condition, past time on the cylinder, this state has some large charge and is generically homogeneous. So the state Q will set a scale mu, probably this is the right way to say it, which is like density 1 over d minus 1, which is much larger than the inverse radius. So the natural scale of the CFT. So now, I mean, it's a fact that when it's a expectation, and once you have scale separation, there will be some sort of separation. Well, scale separation generically implies effective field theory, which is just another way of saying saddle point in semi-classics. So at the same time, if you ask me if this can be rigorously argued in strongly coupled theory, of course, the answer is no. It's based on an assumption, if you want. So I think the basic argument is that this state specifies boundary condition which a clear scale separation. So this is the intuition. Making this argument rigorous would be amazing. I don't know to do it. So I think.
For instance, sorry, just like a stupid question. In strongly coupled theory, this is hard to prove. For instance, in free theories, is it still okay? Like, does this?
The theories, the semi-classic works, but it's boring. I mean, in theories with moduli, there is semi-classics, but it's different. It has semi-classic, it's just like delta Q going like Q. And okay, if I let time, I'll argue more in detail why this must be the case. But it's not a contradiction to semi-classics. It's rather a contradiction to, well, to the fact that generically you only have this symmetry group. In the cases we have models, we have more symmetry. That's not an explanation.
Thank you.
No, but thanks for the questions. Yeah. So okay, I was just saying that anyway.
Gabriel, can I ask a question? So you said when you have model, we have more symmetry, but suppose we just have more symmetry because the symmetry group is larger than U1.
Mm-hmm.
What would change then?
I mean, not much. Well, I mean, I think not much a priori, just that, you know, well, here is either U1 broken, either U1 unbroken. Instead, if you have a larger symmetry group, you can partially break the symmetry group or fully break the symmetry group. And which option is realized depends at which operator you're looking at, so the representation of the state, and also on the theories. Like, for instance, in the UN model, like to make something concrete, in the UN models, so when you replace U1 with UN, you still expect a similar picture. And you can argue, for instance, the epsilon expansion, that a similar picture exists, but the internal symmetry group is not fully broken, it's broken to ON minus 2. But you can imagine a different theory with ON symmetry, which in the superfluid phase, the symmetry group is fully broken. So what changes is that you have more possibilities depending on how you break the internal group. Is that an answer or no?
Yeah, thanks. Thank you.
Okay. Okay, so anyhow, just I was remarking here that one loop contribution here is somewhat theory independent, and in the odd theory is really calculable. In the even, it's renormalized by some classical contribution, which doesn't mean that there is nothing calculable. It just means there will be some logarithm of the running scale that you can compute, and their cutoff scale is Q to some power. So in the equal 4, you find this universal result. And again, most of what I'm saying here just comes from this paper by Hellerman, or some extension here and here. But okay, you might say this is a sub-bleeding prediction, you might say it's boring. So let's look at something perhaps more interesting. So another thing that you get very easily is that if you expand just your path integral into fluctuations, you have just a Goldstone model, as I said, and its dispersion relation is fixed by conformal invariant. So it's like 1 over d minus 1 times the eigenvalue of the Laplacian on the sphere. This, if you want, this 1 over d minus 1 ensures that the energy momentum tensor is traceless. So, okay, so well-known fact, superfluid. And this Fock space naturally gives information about the spectrum of states with the same charge Q, and yes, and different angular momentum. And it's just a Fock space in terms of these guys. So Fock states with angular momentum bigger than 1 provide new primaries, and the standards must be there, and they are nicely provided by the J equal 1 creation annihilation operators. And this can be shown by an explicit calculation of the generators, or more simply by exclusion, because these are the only one that have omega equal 1. Okay, this is another way to understand why this must be 1 over d minus 1, because you want omega equal 1 equal 1. We want omega j equal 1 equal 1, sorry. Okay, so this concludes my review of Hellerman work. So I just want to take 5 minutes to list some work which has been done, which is ongoing, on how to generalize it. Already partially mentioned nodability symmetries, and I think the first paper they were systematically studied, again, the EPFL paper of 2016. I'll have quite a bit to say about large charge and large spin in a moment, but so I'll skip it for now. An interesting ongoing work, still in the context actually of the epsilon expansion, but I think applies more generally in effective field theory, concerns Lorentzian observables. So how to do conformal collider physics in large charge states. And this is work ongoing by PFL student Firas, Hashemoni, Claudio Tazzi, and Matthew Walters. Okay, I think I should refer you to them if you have questions. I mentioned that there is superfluid is not the only possibility. So other things that were explored are theories with moduli. I hope to say something. This was essentially this series of work between 2017 and 2021 by Hellerman and collaborators. And recently also free Fermi spheres, and there is some ongoing work on interacting Fermi spheres by people, Snorre Komrogotsky, Mark Mezzeis, Philippe Pal, and Javier Aviv. Obvious generalization entail like non-ratistic conformal field theories and boundary defect conformal field theories. Going a bit more towards the abstract direction, and there's been very few work. And again, I think that not because it's not interesting, but just because I said at the beginning, with respect to the large spin, it seems harder how to devise how to make all these works into abstract form. But there's been a unique attempt at a bootstrap analysis in this paper by Jaffel, Mujanov, and Zhiboyadov, which is very interesting. And there is some work, and there is also some ongoing work in Monte Carlo simulations that I think so far that I think is not conclusive enough to say whether the O2 strongly coupled model is really in a superfluid phase. But if you're optimistic, you might think that this work actually computed for you the first two Wilson coefficients of the effective field theory. Okay, I'll have more to say in the conclusion, I think. So since I started with large spin, it seems natural to me to ask, what about spinning operators at large charge? And now this regime should connect with the Aldheim-Aldacena regime I mentioned at the beginning. And this will be some old works and also some new work. First natural thing to do in this context is to look at the states that you have written the effective field theory. Since we don't know how to do bootstrap at large charge, let's try to do this. And okay, you find that you can start states with a single phonon of spin J. And sorry, I'll be working in 3D, and I'll have in mind you to model just a concrete theory, but that's not important. So you can take a single phonon with spin J, or n phonons with spin J over n. And the first case is more favorable, but it is with CFT only for spin much smaller than the cutoff, which is square root of Q. And phonons, you can sprinkle them over the sphere. So you can extend, you can go a bit beyond J or the square root of Q. Actually, you can go up to J or the Q to the 3R. So you might be tempted to conclude that this is your answer for the at large J for the minimal energy states at large charge and large spin for J much smaller Q to the 3R. But there is a reason, but one should be suspicious about it. And the main reason to be suspicious is that, in fact, we know that physical superfluids, when you make them spin, they will start developing some solitonic profile rather than only phonons, and particularly develop vortices. So first you see here is the superfluid at rest, then you make it spin a bit, it develops one vortex, is this black point here, then a bunch more, then more, etc., etc. And I couldn't find the reference for this picture. So if anyone knows, please let me know. Just found it online. So you can start looking for vortex solutions in your effective field theory. But in fact, there is a more convenient way to do that, to systematically incorporate vortices in the effective field theory. So I want to quickly describe it. So to see whether vortices are really the right thing to look at for large spin states in the superfluid, let's try to write an effective field theory for them. So we dualize. To do that, it's convenient to dualize the scalar description in terms of a gauge field. That's something, it's just a Legendre transform. And as it is well known, the relation between these two descriptions is given by the U1 charge being equal to the topological charge on the gauge theory side. And therefore, the charge Q just translates into a monopole magnetic field B on the gauge theory side. So now it's essentially the magnetic field which sets the cutoff of the effective field theory. Okay, that's just what it is. Vortices can be, which are some solitonic solution on the scalar side, just become charged particles on the dual side. And you can easily write them systematically in effective field theory following this paper. And just by dimensional analysis, the mass of the vortex, so the term in front of the, so it will have two terms, the gauge coupling and it's not Namugoto, the word line action. And the mass of the word line action, just by dimensional analysis, can only be square root of Q, or square root of the magnetic field. And this means that physically vortices, so charged particles in magnetic field, will arrange in Landau levels, separated by B caps of B over M, which are again order cutoff. M is square root of B, so this is order square root of B. This means that effective field theory will apply only if we integrate out all Landau levels but the first. So this means that we will have an effective field theory for the lowest Landau level. This is something very well known condensed matter, but in practice, if you didn't know anything about Landau levels and stuff, you could have arrived at the same conclusion just by noticing that the last term is higher order in derivatives. Because the first term actually, you know, a mu has some fixed value because you're in a monopolar background, so we'll have a term a mu x dot mu, so it's first order in derivatives. This instead, up to a constant term, is order x dot square, so it's order velocity square. Let's say ai x dot I. So the second term is clearly higher order in derivatives, and you can neglect it. So there's no mystery here. But physically, the picture is that you have particle magnetic field, there are Landau levels, and the effective field theory only apply on the lowest Landau level. Questions? Okay. So now the problem is an electrostatic problem.
Well, I guess you went a bit too fast, at least for me. So these particles are the vortices, and so you're trying to determine how many vortices you're going to put into the system.
Okay, so that's a good.
What determines the number of vortices?
That's a good point. So I should say QP, the charge, is equal to the vorticity. The vorticity is the winding around the configuration. For instance, a configuration where the Goldstone is pi equal L phi has vorticity equal L, which of course belongs to, it's an integer. So now the strategy, what's the strategy? You should try, and the vorticity is quantized, so it cannot be smaller than 1. So now you start to add, you should just look around for configuration with vortices and comparing them, find which one is the one is minimal energy. That's not that hard because I'm going to argue in a moment that vortices with minimal charge are favored over vortices with charge which is larger. So to leading order for the, you will look states with 2 vortices. Then if you want to increase angular momentum, you look states with 3 vortices, and so forth, so on. And then you will try to arrange them such that there is a ground state. I'm just saying that the strategy is just considering 2, 3, 4 particles and look which one of them has minimal energy, and it will turn out to be the one with smaller number of particles, but at fixed angular momentum. So 2 particles will not exceed angular momentum q, 3 particles will go angular momentum like 3½ q, and so forth, so on.
Well, I'm a bit confused why the vortex mass is not going to enter this calculation. Like so, if you just put one vortex, yeah, you created some vorticity, but you also created some energy just because the vortex core isn't this the right intuition?
Yeah, so that's a good point. So the vortex mass in some sense enters, but okay, let me think. Let me think is the quickest way to answer. No, that's a good point. So the reason why, so every vortex starts energy square root of q in the core, but there is actually a larger contribution which you can interpret as a normalization of the mass coming from the self energy of the vortex. So 2 vortices, say charge plus and minus, interact with the electric field, but they also have some self energy. The self energy leads to a effective contribution to the mass, which is one loop x out, which is square root of q log of the cutoff, log of q. So this contribution to the mass, which I'm keeping effectively, is the one which is going to dominate.
Okay.
Times the vorticity square, by the way. Sorry, this is why in one vorticity one. So, but you're right. In some sense, I'm keeping the mass because I'm keeping the trivial piece of the border in action, which is renormalized by this self-energy.
Okay.
I think you're right. Okay, so anyway, I'll try to explain again a bit these things in this slide. So if you miss them, I'll for the others, not for you, Slav, of course. And so the point is the problem turns out to be an electrostatic problem. So this equation is just telling you that electric field should be balanced by V wedge B. So the Lorentz force should be 0. And this is because I'm neglecting terms which are second order in the velocity. So there is no acceleration in the equation of motion. And V is the velocity of the vortex, of course. And the electric field is set by Gauss law. So if you solve this equation, you find electric field is order square root of Q. So it's smaller than the magnetic field, which is order Q. And the velocities will generically be small unless the vortices come very close. So we are dealing with non-relativistic particle in some electric and magnetic fields. So it's really an electrostatic problem on the sphere. And you can compute in closed form energy and angular momentum for the vortices. And that's what we will use to find the lowest energy configuration. So the energy looks like this. So this is kind of RP is like you imagine embedding your sphere in the three-dimensional space. And RP is really the coordinate, the R3 coordinate in the free embedding of S2. But it's just the solution of the Laplacian if you want, because you have a Coulomb potential between vortices. And the log Q, this comes really from the self-energy. So if you want this term here, if you use the Gauss law, you can rewrite it as something like square root of Q, sum over P, Q squared P, log Q. So this is the term I was mentioning to Slava. Will eventually tell you that you want to have QP minimum generically, so QP equal 1. And you want to have as few vortices as you want. So this is the leading term to the mass. And the angular momentum is somewhat mysteriously, unless you're familiar with fuzzy spheres, turns out to be proportional to the coordinate of the vortex times QP, which you can physically interpret as each vortex being a monopole harmonic of angular momentum Q half. And the angular momentum is just the sum of the angular momentum of all the harmonics. This just comes from Gauss law and from the expression of the angular momentum in electrostatic, if you remember being wedge B, or schematically. But okay, just a calculation. And B is constant. So, okay, so you stare a bit at these formulas. And the natural thing, as I said at the beginning, because of this fact, is to look at configuration with only two vortices and minimal charge. And this is a vortex-antivortex pair. The angular momentum is equal to the distance, and you find that this configuration is indeed convenient over the phonon when J is much larger than square root of Q and smaller than Q. Since the leading contribution to the energy comes from the gauge interaction, which depends only on the vorticity, which is fixed here, you find that to leading order, the answer depends on a unique parameter alpha, which is the same one from which the superfluid energy depends at leading order, and takes this form here. So again, this J square over Q comes because J is proportional to the distance, and you have this Q in the formula before. Because of the self-energy, as I said, when you increase J much larger than Q, it's convenient to have a number of vortices which is much larger than 1. And here the strategy then is symbol. Let's just try to approximate the vortex density with some continuous distribution and minimize the energy at fixed angular momentum in terms of this distribution. And you find a result, which is this one. And you find a density which indeed increases like J over Q. And this nicely matches the experimental picture I showed you before. So I think one can be kind of, okay, there was no guarantee that relativistic superfluids on the sphere should match non-relativistic experiments, But the point is that that picture follows some few basic facts, like the fact that the fugacity of the vortices depends on their charge, and therefore it's kind of reproduced here, and we can make some very precise predictions for the energy of the ground state. As J approaches Q2-3 the effective field theory breaks down. And
what is alpha here?
alpha is a Wilson coefficient. Yeah, alpha is a Wilson coefficient, and it's the same Wilson coefficient of the superfluid energy. So the energy of J equals 0 will just be alpha Q2-3 alpha plus correction. So if you believe this picture, this is the same one which has been computed by Monte Carlo. It's
okay, thanks.
Okay. So I was saying as J approaches Q2-3 alpha, the effective field theory breaks down because vortices become relativistic. So the question is that can we nonetheless go beyond this regime? So as J, the question, if you want somewhat, is when should we expect this effective field theory to break down and to recover a pictural Aldheim Aldacena? And one might think this happens now because delta will become, J will become of order Q2-3 alpha, which is of order delta. Sorry. But, you know, physically it doesn't seem very right because you still have a superfluid spread all over the sphere, while Aldheim Aldacena has some particles which are rotating on the equator. So there should be also the spectrum of excitation here is mostly given by phonons and some vortex lattice displacement. And it doesn't seem to resemble at all the Aldheim Aldacena excitation which are simply just a mount in a multitrace picture to displace derivatives. So there should be a pretty violent transition if you want to go from here to the Aldheim Aldacena picture. So I think it is more reasonable to expect that there should be a next phase still within the superfluid in some sense, which interpolates between this vortex distribution and the Aldheim Aldacena multitrace picture. And I'll show you now some results about it that are encouraging. The first fact again okay, this is just because that's where I think that's what's very helpful for me in this presentation, but perhaps it's not very helpful to understand. But if you look at experiments again, and you put now your Bose-Einstein condenser again, you trap, you make it spin, at some point, you find a transition from this vortex lattice state to a coherent state. So a coherent superfluid, which is localized on an annulus, which you can think of as a vortex with giant core. And the reason why there is this first order transition is essentially that when the vortices move faster than the speed of sound, there is some kind of super radiant instability. I don't think it's something that can be analyzed within effective field theory, but it's pretty much like when an electron moves faster than the speed of light in a medium, you have Brent-Strahlung emission. Same thing, if something is moving faster than the speed of sound in a superfluid, it will emit many quanta, and this will trigger some first order transition to a new state. So, okay, this is the intuition. And I think very nicely, this is what happens in this simple effective field theory. So, at least when J over charge is an integer, you have a natural candidate for the giant vortex in the U2 model, which is a superfluid solution which is localized around the equator. So the charge at some point drops to 0, and you are here, blue is vacuum, and red is where the superfluid is very dense. And this is, if you want, again, you can think of this as a vortex with giant core, just that you have now a core on the north and a core on the south pole. So it's really the stereographic projection of this picture here, if you want. So it's really nice. And the difference with respect to before is that now I'm taking the vorticity L to be very large, so to approach the chemical potential mu. And okay, this is a solitonic profile. And notice that since the superfluid is coherent inside here, the right thing is to use now back the scalar variable, not to work in terms of dual gauge field. Okay, so, okay, I don't want to tell you too many details. I'm going to show you the results, why this is encouraging towards the idea that this should be the last step in matching the Aldheim Aldacena, in going towards the Aldheim Aldacena picture. And again, it turns out that for J in between Q2-3 alpha and Q square, you can compute the energy of this state. It is the ground state if you compare to other solutions you can find. And it goes to leading order linear in J. So it starts to resemble the Aldheim Aldacena picture. And it kind of makes sense. Well, diagonal descent has many particles localized on the equator spinning. And it makes sense that there is a regime where they're still coherent enough that you can think of them as a superfluid. So this is the conjectured operator corresponding to this one. You have some corrections. And again, alpha is the same parameter of before. And there are a bunch that all depend on alpha and that you can compute. There are also some correction which depends on new Wilson coefficients that you can parameterize. And okay, this is in progress work. I think even more encouraging is that if you look at the spectrum of fluctuations and in first instance neglecting correction of j squared over q cubed, I'm thinking j much larger than q to the 3 half. And in this limit, it matches precisely what you would expect again from a multitrace, because omega is equal m, which is the azimuthal number of the angular momentum, plus n. N is some integer, positive integer. M is not necessarily positive. And the fact that the spectrum is integer spaced, again, is precisely the idea that you can add, subtract, or contract derivatives in a multitrace state. So this state here seems to really be the already a multitrace state in some sense. You might be worried that if you take, since M can be negative, that this state is unstable or the ground state is highly degenerate, but this is just an artifact of this approximation here. So if you restore the first correction q cube over j square, you find that indeed you have a unique ground state and that the gap is given by this formula here with respect to the lowest lying state, which has the same spin j and charge of the giant vortex. Okay, so the message of this long detouring charge spinning operator is that I think we now have a complete picture, at least to the extent that effective field theory can give you, of the lowest dimension operator, fixed charge, and angular momentum J in the O2 model. And this is to leading order just a superfluid with perhaps one phonon. Then is given in between J square root of Q and Q star by some vortex anti-vortex pair. In this regime, we will have some many vortices. Eventually, we will transit to a giant vortex state. And eventually, we expect that at this point here, the natural thing is that now, yes, you will have an all-diagonal descent multitrace with correction, which follow from the Yukawa potential exchanges between the many particles. And this has never been made precise into effective field theory, but you can easily estimate that the correction will go like this. Okay, so if there are no questions, I want to tell you we really have 2 slides on moduli spaces, and then I'll conclude.
Can I ask a question?
Sure.
Do you know if there is any analog of the Aldheim-Aldacena multitraces in the experiments?
I don't think so, because already, so this experimental result, which actually, sorry, I forgot that I wanted to give credit to the people here. This is result 2019. It went on a Popular Science Journal 2020. This is from the journal. This is the experimental. By the way, giant means 50 micrometers, just something like that. But these are very hard to obtain, these results, because you have to make the trap spin coherently and while keeping the temperature low. So I don't think there has been any interest towards going beyond this. And yeah, so I doubt that people looked at it. Also, I mean, I should say here, the critical sound speed is the speed of sound, which is much smaller than the speed of light. Instead, in the Aldheim-Aldacena picture, stuff is moving at the speed of light. So it's not clear that the 2 things really are the same. The relativity, I think it's important in the Aldheim-Aldacena picture.
Okay, thanks.
But okay, yeah, thanks for the question. I want to give credit to the experiment. So, okay, most of let me now go back to something which is not my work, again, to Simon's work mostly and collaborators. So I mentioned that a slightly different phase at large charge can be obtained for theories which have a moduli, which have a modulus. And so the basic picture, in fact, is independent of any supersymmetry or anything else. But of course, we all know the only natural cases are the one with supersymmetries to the extent that we know, or I know at least, in d bigger than 2, at least. No, I think I will always. So let's consider CFT4 with a moduli space in which the U1 symmetry is broken. And now, I mean, at a generic point of the modular space, the theory is well described by some axiodilaton plus some other degrees of freedom, which possibly, which I denote CFTIR generically. And this is the effective field theory. So the Archimedean is essentially a free scalar, the CFTIR, and some irrelevant couplings between the two. And here I stress that the Axiodeton EFT is kind of funny if you don't specify more, because a priori there is a term that you can write lambda phi for, which is incompatible with the saddle point you want, which is phi equal b. So this is the famous statement that theories with moduli spaces have some tuning, and this is how you see it in the effective field theory. You have to tune this to 0. And normally this is achieved, of course, by some symmetries. However, once we have this effective field theory, the same effective field theory should apply whenever the path integral is picked around a configuration where the field web is much larger than the derivatives of the field. So we shouldn't use, state is effective field theory. They don't work on a single state. They work on many different states as long as the derivative expansion works, at least physically. So among these states, this includes a state which has the next to simplest solution of a free field theory equation, which is V over x squared, which if you map it on the cylinder is just, and you go to Lorentz, it's just kind of a superfluid again, but with very tiny chemical potential. So chemical potential 1 over r. So I think physically it's a bit incorrect to call it a superfluid. And now if you plug back into your action and notice that all your interactions are irrelevant, in radial quantization, this corresponds to a state which has charge Q proportional to V squared and energy proportional to Q, just because the effective field theory is a free theory to leading order. So this tells you that the large charge sector of theories with moduli space, at least physically, you can think it's associated to some different behavior. And I think I should say this has been first pointed out in this paper by Hellerman, Maeda, and Watanabe. Okay, so it's just a simple argument. Of course, I mean, now if you want to make prediction for the theory away from at the conformal point, you should specify some theory and specify some effective field theory more precisely. And of course, most of the application, at least the most spectacular one in the context of n equal to 4-dimensional superconformal field theories. In this case, operators with large U1R charge can be described by some Coulomb branch effective field theory. And the nice thing, okay, I don't want to go too much into detail in the effective field theory. The nice point is that it has only 2 F terms, meaning only 2 terms whose coefficient is protected. One is the West zoom in, and one is the kinetic term. And these are the only operators which contribute to certain class of observables. So you have the energy of the ground state is protected by supersymmetry, so it's a boring quantity. But OP coefficients of Coulomb branch operators are not boring and can be computed in a large charge expansion. So they are associated with some 2-point function because normally one works in some normalization where some OPs are normalized to 1. And through this finiteness of the F term and the Todd equation, which is someplace follows from localization, people could compute within effective field theory the full series in 1 over n, so in 1 over the charge, up to exponentially small corrections. I think this is this paper here. And this prediction has been verified and in fact extended to large extent via some localization analysis in a double scaling limit, very analogous to the one I described in the epsilon expansion by Grassi, Komorowski, and Tizzani in 2019. And remarkably, they found that these results can be obtained within a dual matrix model. Okay, so this is just flashing some highlights. Okay, so this concludes, I think, my overview. So, okay, just let me say what are the take-home messages. So the idea is that generically, one expects large charge operators to admit some universal effective description. This effective description, in the case we have a weak coupling, is associated to a semi-classical trajectory and to some double scaling limit, in many examples at least. These ideas can be used to argue and find the scaling dimension of the lowest dimensional operator with fixed large charge Q and angular momentum in the 3-dimensional 2 model. And the correlation function of large charge operators in theories with moduli spaces are computed using the same effective field theory which applies on the modules of the theory. So for future work, okay, I mentioned Fermi liquids, and I think there is still some work to do there. which might turn out to be just technical or might turn out to have some interesting consequences. And it's just mostly to do about relativity in Fermi liquids. I totally excluded holography from my slides. And this is not because I have any prejudice or anything, but just because it's very confusing. It's because it's very confusing in this context. And that actually something should be nice to discuss. And what happens in holography is that all solutions we find, including boson-stars holographic or holographic superconductor in the Poincare version that are claimed to be dual to superfluids on the boundary, as soon as you turn on a very tiny little temperature, they have order n square entropy. So this means that even at 0 temperature, they cannot be described by a single Goldstone mode. And even though some papers claim otherwise. So there is a puzzle of what's going on in holography. Why are there so many degrees of freedom which stay light all the way until 0 temperature? Is it an issue about T to 0 limit and N to infinity limit? Or is there something deeper that this is teaching us? And even more about Reisner-Nordstrom black holes, that it's by now pretty clear, for instance, from the work of Ilyes and Turashi, that the effective field theory up to very low temperature of these guys has order n square, even more degrees of freedom. So, from this viewpoint, they seem to be very exotic states with a lot of degrees of freedom even at 0 temperature. And okay, I don't have much to say. They are confusing to me. Perhaps more concretely, one can ask whether we can bootstrap the effective field theory. And by that, I don't mean really deriving the effective field theory from the bootstrap. That's probably very too ambitious. But a very ambitious question, which I hope someday we'll find the question, is how to use crossing to find the Wilson coefficients of these effective field theories. And this is a physical question. You can also, a related question could be how to use crossing to find the viscosity, which controls some heavy, light, heavy OP coefficients. And in general, how do we use crossing to go beyond the vacuum regime of where only correlation function of light operators are important? So, and there are some ideas in this paper again, which I mentioned before. So finally, I said that the Monte Carlo measurements tell us something about the energy of the ground state in the O2 model at large charge, but for some reason, they did not measure ever the first excited states above the ground state. And if that were to agree with the prediction of the large charge EFT, I think that would be a smoking gun that the O2 model, even a strong coupling, is really in a superfluid phase. And hopefully this will be done in the future. And especially Banerjee and Chandrasekaran are working on related issues. So this will be, it's not for this audience, but something will be hopefully done. So thank you all for the attention. Let me go to the question slide.
So your problem with Monte Carlo is not that they have any mistake. It's just that you did not measure the observable that you would like them to measure, because they saw pretty nicely this.
Yeah, but
3/2 growth.
But the 3/2 growth is really by the existence of a macroscopic limit. You can imagine a strongly coupled, like Reisner-Nordstrom black holes have the same Q to a 3/2.
But you said yourself that there is nothing else that you can imagine apart from Fermi liquid and superfluid. And,
but I don't want
now you kind of turn this around and say, oh no, well, actually something else.
I don't want to rely only on my imagination as an effect of effective field theorist imagination, in the sense that, these examples here of holography are anyhow somehow worrisome from this perspective. Because, you might say they are just large N artifacts, but maybe not. So it's not really no. So I think that having a prediction for the energy,
How about if they measured the order 0 coefficient, because they did not, their precision was not enough to measure that. But
right.
if
If they had measured that, that would be, if they had measured that, that would be equally smoking gun. I agree.
Okay, sounds good.
Yes, is there a question?
So in your examples of calculating scale dimension at large charge, there were, I think, no non-trivial mixing effects. Are there potential areas in which mixing effects will become significant?
You mean in the epsilon expansion?
I was thinking in the operators, mixing of, if there are two operators which are essentially degenerate, then when this degeneracy breaks and due to...
In which context? You mean in the epsilon?
Well, I mean, suppose you were calculating the scale dimension of large charge operators, but the sub-leading contribution at large charge, I mean...
Here.
And then there would be more than one operator in the sort of perturbative expansion at least.
So in all the examples we computed, there was a unique ground state. So in the epsilon expansion, you have phi n cannot mix with anything else because it can only mix with states which have the same U1 symmetry. In the effective field theories, whenever whenever you find a solution, you try to check whether it's the unique ground state. You just have to check against other classical solution and against perturbation. So I think throughout my talk, I apologize if I gave the wrongest impression. I think I always find a unique ground state. What happens in perturbative theories when you can have mixing, you say at 3 level, there you can imagine some more complicated perturbative theories when you have, say, 2 charge n operators with the same screen dimension at 3 level, is that generically this at higher order in the loop expansion, they will be disentangled, I think. So if you do the semi-classical approach, you will collapse towards the true ground state. I think there are some examples in the literature.
Right, yeah, I was thinking if you were trying to calculate the enormous dimension of some operator phi to the n phi bar when n was large. I mean,
okay, so I didn't discuss that. Okay, so that's a good question. Right? I didn't discuss that. So, but so these operators you're mentioning, they will be associated to fluctuations on top of this background. So you will add some fluctuation here and some fluctuation here. And then you will study the spectrum of this fluctuation from this. By the state operator correspondence, it will be a spectrum of the operators, you say. And you find that as soon as you turn on as small, tiny, non-zero lambda n, so lambda n bigger than 0 but small, all this mixing are disentangled. So meaning the tree like phi n. So you might imagine, for instance, a mixing phi n, phi bar phi, yes, versus phi n, I don't know.
we can have some derivatives.
Exactly, some d2 phi n. You find it as, by computing the spectrum of the fluctuation, these two guys, as soon as lambda n is non-zero, there is no mixing. So in other words, the perturbative correction lambda n disentangle the mixing. And this is already here in the classical solution. So in the leading order in lambda, but all orders in lambda n.
Okay.
But yeah, there are somewhat non-trivial expression for the dispersion relation of these guys that all through they are, but there is no, beyond the free limit, there is no mixing issue.
That's a little surprising, but maybe.
Why? I mean, we know that at one loop, this mixing will be lifted, right? Generically.
Well, typically in perturbative calculations, you have to diagonalize a matrix, which involves.
Yeah. Here I have to diagonalize the spectrum of this fluctuation. So the quadratic Lagrangian will be something like pi r, and then some matrix and some operators. So if you want, it comes from the diagonalization of this matrix. We'll have some d2 constants, d2 stuff. So okay, there is some diagonalization. So the only powerful thing is that you do it once and for all these states here in this approach. You don't have to diagonalize every time at each level. So in this sense, yes, it's surprising that it's so powerful.
Can you compare your approach to some of these papers by people around Hellerman that you cited? Because I understand kind of the effective field theory, the way you do it, but for example, some of the papers that you cited, like the one with Alvarez Gomez, for example, yeah, I just, when I open those papers, I cannot understand anything. It's just to understand those papers, because they are written not in effective field theory language, but they're written in a purely like Lagrangian manipulation language. They deal with Lagrangians with scalar fields, and they're trying to make there some statements which they claim to be generally valid. So I don't understand. Can you confirm those papers independently with your analysis, or do you understand that it's equivalent?
Okay, after having quickly checked, no one. Okay, I think those papers are not the clearest papers on Earth, to say it politely. Let me think. I mean, I think what they're trying to do, I think that's the way I understand it after having looked at many of those. They start from some semi-classical analysis of some model, which is some weakly coupled model. It's not the true model they want to study, but has some resemblance. For instance, you can take, or you can neglect quantum effects, and then they use that semi-classical analysis or unjustified analysis to motivate some effective field theory description. But I don't think honestly that there is any way to derive effective field theory, if not, this set of assumptions which I tried to spell out here. So I cannot see any other ways but this to have a controlled idea of what you're doing. I would say what I'm doing here, it's rigorous, but it entails some assumption which I'm spelling out in the slides, for instance.
Mm-hmm.
I don't think there is any other way to bypass this. There might be other ways in which you think at a problem for the first time that I can understand.
So I remember in particular there were some issues where in presence of bigger global symmetries, whether the ground state was homogeneous or not, or something like that. And they were trying to argue or prove, quote unquote, that in some cases it was not homogeneous. Precisely, I was like wondering,
okay,
you're saying if you can actually prove anything, or was it a guess?
Okay. I strongly disagree with the approach of that paper. I think I told them. And no, okay. So the question in particular, to give some context, was in the context of the ON models. And what you can say, you're computing the path integral between a traceless symmetric. So let's say O4 to have something very concrete. So O4 has two charges, so traceless symmetric state, Q half, e to the minus ht, Q half. So now you might ask, if this path integral is semi-classics, and what is the symmetry breaking pattern induced by this state? And well, you can argue, for instance, from the epsilon expansion, from the large N, or you need to make a guess here. And the reasonable thing to do, I think, is look at the epsilon expansion. And that the symmetry breaking pattern is O4 going to 2. And then you extrapolate. Let's assume this is the symmetry breaking pattern also in 3D, not only in 4 minus epsilon. So this is true for sure in 4 minus epsilon. And with some extrapolation, we believe it's true in 3D. You can question it. I have no better justification than this. Now, say you want to look at the energy. So you want to look at the gap of the state Q half with energy somewhat excited, like Q half plus 1 half, Q half plus 1 half, minus delta Q half. So let me not say what they're doing because I don't like it. But I think the natural thing to do is ask, is this state with this, Q half plus 1 half is still a traceless symmetric, sorry, something like this. The first mixed symmetric operator you can think of with respect to the ground state, traceless symmetric. And now you can ask, do I have degrees of freedom which follows from this symmetry breaking pattern that can interpolate this state, so that are charged under the unbroken O2, for instance. And the claim is that this state here, and that's an unpublished claim, that's why I didn't wanted to cite it, this is what is called in finite density system a gapped Goldstone. In particular, gapped Goldstone with angular momentum equal 1. And this makes sense because the first mixed symmetric operator in the epsilon expansion entails some derivatives. So it makes sense it has some angular momentum. So, and this gapped Goldstone naturally follows, and it is, despite being gapped within effective field theory, just from the assumption of this symmetry breaking pattern. So once you assume this symmetry breaking pattern, the rest follows. So again, just from the universality class. So in this sense, since it has angular momentum equal 1, you can claim that it's inhomogeneous. Pretty much as any Vogt state is really inhomogeneous. So I think this is the way to interpret the inhomogeneity they're talking about.
Okay.
But if you find an explanation along this line, you will not find it in the literature. Yeah, I think.
Oh, but you can do Q over 2 plus J over 2, comma Q over 2.
Q plus 2 over 2. Yeah, I can, oh, sorry.
You can do Q over 2 plus Q twiddle over 2, comma Q over 2. Then you won't be able to describe it in effective field theory with translational invariance for large Q twiddle.
Sorry, sorry, I didn't get what you're saying. You want to do Q over 2 plus?
Q twiddle over 2,
Yes.
comma Q over 2.
So my claim is that this is within effective field theory for Q twiddle much smaller than Q.
No, of course, but now suppose you scale them both in the same way. Then it genuinely requires a non-translationally invariant ground state, like a solid or something.
Yes, but then yeah, okay, but to my understanding, okay, but I no one proposed that to me a reliable construction of this ground state, I think.
Well, that's a very interesting open question. It might be one of those striped ground states or a condensed kind, maybe a solid ground state.
Okay, no, this is a good question. A state like this, you would expect it to be inhomogeneous, and if you relax what I would, but I mean, the claim of Ellerman was really for the state where, or the claim in the literature is really for Q twiddle equal 1. I'm saying that
Of
claim.
course, that is just
that claim is plain wrong. I'm saying this claim
of
you're
course.
okay.
For Q twiddle equals 1 is just a particle on top of a homogeneous ground state. There's nothing mysterious about it.
I mean, the point is that since these are these gapped Goldstones, they were not included in their effective field theory. So you should be very careful about chemical potential and stuff. It's easy, but I think there are mistakes. That's what I'm saying. But yeah, the regime where Q twiddle is of order Q in the O4, in O4, I think it's an open question because it's clear that the superfluid effective field theory breaks down. So, so there is an assumption which I didn't spell out here. I forgot that. Sorry, this is an important stuff, and I don't know what I'm doing here with that Q is scalar, so that Q is homogeneous. If you violate this assumption, you can start having richer ground states. And this is what Zohar thinks applies in the regime where Q twiddle is of order Q in the O4 model, I think. So, but if you don't violate the assumption that Q is homogeneous and scalar, I think, yeah, that's all you have. Sorry, this was a Lambda 2.
Any other questions? Well, it was very interesting talk. Thanks, Gabriel, a lot. So let's thank Gabriel.
Thank you.